In space, there's a lot of darkness, until there isn't. When a star dies or merges with another star, it produces massive amounts of energy. This energy can be so strong that it reaches out through the darkness, like the hand of God, to tell us information about those explosions in space. Those explosions, called gamma ray bursts, or GRBs, emanate from distant stars on the wavelength of 10 to the negative 10 to 10 to the negative 12 on the light spectrum. Since they have such short wavelengths, they are very quick when they come, but they do not move faster than light. So when they reach us, they can still be thousands of years old. GRB tracking, as we know it, starts in the 1960s with American fear. At the time, we were so terrified of a nuclear threat from Russia that the Department of Defense launched a project called Vela to detect Soviet explosions around the globe. Rather serendipitously, though, these satellites ended up detecting the very first GRBs, observing inexplicable short-duration flashes of gamma radiation in deep space. This phenomenon was inconsistent with any known nuclear explosion or Soviet event, and the discovery was published in the astrophysical journal Letters in June of 1973, shifting the understanding of astronomy and leading to the recognition of GRBs as powerful distant cosmic events. Fast forward to 1991, NASA launches the Great Observatory, also known as the Compton Gamma Ray Observatory, specifically designed to detect GRBs using their Burst and Transient Source Experiment, or BATSI. SEGRO was part of NASA's Great Observatory series, along with the Hubble Space Telescope, the Chandra X-ray Observatory, and the Spitzer Space Telescope. It was the second of the series to be launched into space, following the Hubble Space Telescope. SEGRO did great work in indicating that there was an extragalactic source of GRBs until its deorbit in the year 2000. Before the death of SEGRO, the Italians and the Dutch launched BeppoSAX in 1997, which ended up as being crucial in demonstrating the extragalactic nature of GRBs and detecting their afterglows in X-rays. This was a significant step in understanding of the environment of GRBs. In 2004, on the Delta II launch vehicle, the SWIFT satellite is launched to quickly point its instruments at GRBs and follow up on bursts across multiple wavelengths. From gamma rays to visible light, SWIFT can determine the origin of those bursts and study their evolution. Headed by principal investigator Neil Gehrels until his death in February 2017, the mission was developed in a joint partnership between Goddard Space Flight Center and an international consortium from the United States, United Kingdom, and Italy. The mission is operated by Pennsylvania State University as part of NASA's Medium Explorer Program, or MIDEX. The SWIFT satellite was an improvement upon previous satellites because it could detect bursts around 100 per year, and it could even detect those bursts if they were approximately 3 times dimmer than previously detectable. While originally designed for the study of gamma ray bursts, SWIFT now functions as a general-purpose multi-wavelength observatory, particularly for the rapid follow-up and characterization of astrophysical transients of all types. In its place, however, NASA launched the Gamma Ray Large Area Space Telescope, now called the Fermi Gamma Ray Space Telescope, to perform gamma ray astronomy observations from low Earth orbit. Fermi's main instrument is the Large Area Telescope, or LAT, which astronomers intend to perform an all-sky survey studying astrophysical and cosmological phenomena such as active galactic nuclei, pulsars, other high-energy sources, and dark matter. However, this can be used to study GRBs in tandem with another instrument aboard the observatory called the Gamma Ray Burst Monitor, used to study gamma ray bursts and solar flares. At last, we have reached the news. As of August 29, 2025, an article in the Astrophysical Journal Letters was published cataloging energetic gamma ray bursts repeating 3 times over 24 hours, making them aggregately 100 to 1,000 times longer than most single GRBs. Those 3 bursts were recorded on July 2nd of 2025 using the Fermi Space Telescope, and they were 3 of 4 bursts determined to be from a similar region of the sky, drawing the attention of astronomers who get notifications to their devices from the telescope to track events such as this one. The authors of the article in the Astrophysical Letters determined that those bursts were indeed from the same location in the sky. While Fermi provides a general location in the sky, better positional data captured by an X-ray telescope called the Einstein probe, a mission undertaken by the Chinese Academy of Sciences, provided a more exact location. Along with the European Space Agency and the Max Planck Institute for Extraterrestrial Physics, astronomers were able to determine where to begin pointing their ground-based telescopes. The team studying this phenomenon suspects that the host galaxy is a few billion light-years away, but research to determine the exact galaxy and distance is ongoing. Understanding that distance will help them understand the true nature of the source. Currently, the authors have considered 2 possible causes for the repeating bursts. One is an unusual type of supernova explosion that lasted much longer than those that typically release gamma rays, and another is a white dwarf, a dead star as heavy as our sun, but condensed to the size of Earth, being ripped apart by a rare intermediate mass black hole. The exact reason for this frequency is still a mystery. However, astronomers have working theories that could change the way researchers understand the death of stars. Is this event really so rare that we've only seen one of them in 50 years? Or is the tip of the iceberg where we might find many more of them if we look carefully, said Andrew Levin, an astronomer at Radboud University in the Netherlands and co-author of the article in the Astrophysical Journal Letters. Because gamma-ray bursts come from the catastrophic death of stars, this might really tell us a lot more about some of the most extreme ways that stars end their lives. The discovery has prompted some, including Dr. Eric Burns, Associate Professor of Physics and Astronomy at Louisiana State University, to suggest that we need more accurate instruments to detect more of these bursts more accurately with new instruments. What we need is to build a new gamma-ray burst monitor that has the deep sensitivity we need, but placing it far from Earth, said Burns. The monitor Burns suggested would orbit at L2, or Lagrange point 2, about 1 million miles from Earth, where the Webb telescope is located. This vantage point is ideal because it enables telescopes to have an unimpeded view of the universe, unlike Hubble, which moves in and out of Earth's shadow every 90 minutes. This type of equipment was suggested as far back as 2021 by the Astro 2020 Decadal survey produced by the U.S. National Academy of Sciences. Burns and his colleagues designed a mission to get such equipment up and running, and won a NASA competition 3 years ago, but it wasn't funded due to budget issues. The team is still pursuing the mission, but it's unclear if it will happen under the current administration. Studying and understanding gamma-ray bursts provides insight into the universe, said Andrew Levin, co-author of the article in the Astrophysical Journal Letters. Within seconds, gamma-ray bursts can create as much energy as the sun does over the course of its ultimately 10 billion year lifetime, he added. Currently, the sun is an estimated 4.6 billion years old. Gamma-ray bursts are like having an extreme laboratory in space, unlike anything that can be built on Earth. Martin Carrillo, co-author of the article in the Astrophysical Journal Letters, said. They can be used to test electromagnetism, particle physics, and Albert Einstein's theory of relativity. Looking out into the void, we only have dots of light to look at. But with better equipment and our eyes attuned to the heavens, we can look through a window into the origin of our universe and the first stars to twinkle brightly in it. I'm Dylan Paul, for Professor Shank's astronomy class, saying I hope you enjoy the view and vote to look out farther.